I ask you, honored Professor Alessandro Margara, appointed as opponent by Aalto University School of Science, to present the observations that you consider appropriate for this dissertation.
Okay, thank you very much. I have some observations, but before I want to say that I'm deeply honored to be here to serve as an opponent. So I met Mikko first last year in DEVS, a conference on event processing. I was giving a tutorial on stream reasoning, and we had long discussions about windowing and how do we see the field evolving. So I found Mikko really prepared and passionate about the topic. So when I was asked to act as an opponent, I was immediately happy, and I replied that I would have been here. So my summary, the thesis addresses a topic that is becoming increasingly popular and important in a wide variety of applicative scenarios: on-the-fly analysis of dynamic information, or stream processing. Stream processing is motivated by the increasing availability of sources of dynamic data, sensors, smartphones, monitoring data, and by the need to timely extract valuable knowledge from such data to detect events of interest or anomalies and to support decision-making. The thesis builds on principles and concepts of complex event processing, or CEP, that aims to abstract simple low-level events into higher-level facts of interest, and studies how these principles can be implemented by relying only on the RDF and Sparkle standards, as defined by the community working on the semantic web. This combination of semantic web and complex event processing technologies combines flexibility of data representation and interoperability of sources with support for dynamic data and timely processing. While the idea of adopting semantic web standards to process dynamic data is not entirely new, and in fact there is a research community working in the so-called stream reasoning domain, very few proposals have focused on integrating CEP abstractions. The work presented in this thesis is the first one that does so by building on standard RDF and Sparkle queries, and in particular on asynchronous networks of Sparkle queries. The novelty of this approach to stream reasoning certainly represents a significant scientific finding in this area of research. All the proposed solutions have been implemented and tested in the instance platform. I particularly appreciated the scientific rigor in the experiments of this thesis, the clear discussion of the experiment data and setup, and the availability of the code and the data sets makes all the experiments fully reproducible for validation and for future comparisons. I also like the validations based on real or realistic data sets that enable for a critical assessment of the benefits and limitations of the proposed solutions and of some of the state-of-the-art approaches. The thesis builds on 5 publications. We already heard about that. Publication 3 shows how the typical operators that build the CEP patterns can be implemented using a network of Sparkle queries. Publication 1 and 4 exemplify this approach using a social application that sends notification when 2 friends are geographically close to each other, and a pharmaceutical supply chain application. Publication 2 proposes a model to represent heterogeneous events in RDF, and finally publication 5 uses networks of Sparkle queries to implement different entailment regimes, and proposes a memory handling solution to the accumulation of data in stream processing scenarios. The proposed approaches have been compared with traditional solutions for stream reasoning based on time windows qualitatively. The thesis provides good motivations to, let's say, abandon the time windows continuous query models in favor of event processing networks. Quantitative comparisons with state-of-the-art CEP engine, ESPER, and state-of-the-art reasoners, Gina and Staldo, demonstrate the feasibility of the proposal, although the non-optimized instance platform is sometimes outperformed by the other tools. So in conclusion, I want to congratulate you on the quality and on the depth and technical depth of this thesis. Okay. Then, can I start with some questions? Okay. So I will first start with some general high-level questions, and then we can go more into the details of some of your publications. So first, my first question was, so basically your work demonstrates that it is feasible to ground RDF-based event processing on networks, asynchronous networks of standard SPARQL queries using the SPARQL updates. However, writing rules and patterns in that way is very flexible, but rather verbose and complex, and requires basically some programming skills. That's something that you also mentioned in your thesis. For example, to properly use the graphs to store the current state of the computation. So somehow in practice, you are almost offering the computational power of an imperative programming language, since you are using the graphs as variables. On the other hand, mainstream data stream processing systems and CEP systems were explicitly built to provide higher level abstractions, declarative abstractions, just to avoid the need to really program those networks. So do you think that writing networks of SPARQL queries is suitable for domain experts? For instance, some specific IoT scenarios? Or you think that it is necessary or suitable to offer higher level abstractions or languages on top of these networks?
I fully agree with your comment that this kind of SPARQL networks and writing them can get complex for domain experts, and that's why I would also believe that we need to develop also higher level abstractions in the language so that we can make it more straightforward for domain experts to produce this kind of applications. One proposal which I only shortly described in the overview of my dissertation is to specify stream descriptions, standardized stream descriptions, which would explain what kind of event objects, what types of event objects will be available in a stream. And one of the purposes to do that would be to enable the platform to understand what kind of event objects will be expected from a given stream. And at that point, it would be far easier to automate actually the generation of the SPARQL query network. So the domain expert who wants to get some kind of event pattern discovered or events processed would not need to see SPARQL at all at that point. So we should build further layer of abstraction on top. Now, of course, this doesn't preclude either that, as there have been many proposals to extend SPARQL with for instance, stream window operators, then I am not negative about making additions. Those could be done, but in my study I have shown that they are not absolutely necessary, that there are other ways to arrive at the same conclusion.
Okay, do you have any hint about the type of language that you would like to see as a higher level language? And do you see feasible or easy to translate those languages into a network of SPARQL queries?
Actually, the first thing that I imagined there was a graphical user interface, because domain experts typically like those. And even though in this RDF format our events can be anything, but in most streams there are limitations of what kind of events there are, that once you have an understanding of what kind of events are being expected, then it shouldn't be very difficult to build even a graphical user interface for the domain expert to define queries on top of that.
Okay. Thank you very much for your answer. So second, so this was more on the level of abstraction. Another question I have is on the processing algorithm. So your work proposes the adoption of these networks of Sparkle queries not only as a language abstraction, but also as a concrete implementation for stream processing or a complex event processing engine. However, for example, in the comparison with Expert that you have shown in your publications, you see that adopt algorithms for stream processing can often perform better. So first, do you think that the level of performance of instance is sufficient in many practical stream processing applications? And then can you maybe elaborate a bit more on which are the main design choices behind Esper? You studied the algorithms in Esper that make it faster than instance, and also do you foresee optimizations that can be adopted from Esper or other ad hoc algorithms and instance?
Yes. So if I start looking at that from the query network point of view, so what can be seen throughout my publications, that instance in its present form is a lower level tool than many of the stream processing systems, because, for instance, these window abstractions are missing. So in higher level abstracted systems where you have a single operator to process the stream, you can have a very short query, whereas in instance you need to find 4 or 5 queries network operating together. Now, as with all lower and higher level programming tools, the benefit is then the flexibility, because you are much more in control. So, for instance, these window-based stream processing systems have a long-standing fight about how the window starting point should be defined. What is the starting point of the first window? Is it using time in the events, or is it using the wall clock, or is it using some other time code? Whereas in developing with instance, I have complete control over which data from the RDF encoded event I am using as my time code. So I have absolutely no problem adopting to different kind of solutions there. So I think that would be one pro in the sense of offering this kind of systems. Now, you also wanted to know about the performance issues in instance and how they are solved with Esper. And maybe we look a little bit back to this slide. So the way that instance has been coded at the moment as a continuously processing retail network, it means that any change that comes into the system is propagated always as far as it goes in the network, and then when you have enough input accumulated, then a result will be produced at the end of the day. And that makes some things easy, but of course other things will be less efficient because there will be computations which were not coordinated. And I think this was a primary example that we found out that once there are 1 million EPC codes in the system, then 1 million comparisons need to be done every time the time moves forward, even though we wouldn't need to do anything about any of those codes in the system. Whereas Esper doesn't check anything unless it gets an input event. So to get Esper to operate like that, I would need to make this kind of time source, pulsing time source for Esper, which would then trigger the checks. But since I was able to implement things in another way, I didn't need to do that. And then in that kind of cases where a lot of data is being buffered, Esper is far more efficient than instance at the moment. Another thing which is a big difference is that I think Esper, this is internal Esper, but then I think it's using these event objects, they're turned into Java objects basically. And there are very, very optimized ways in Java to handle Java objects. Whereas in instance, actually the concept of event does not exist in the Rete network. It only exists in the queries that process the data. So we have a network of data, but our operations on events are not extremely optimized from that point of view. So now going into the performance improvement suggestions, the current implementations of instance have been done on Common Lisp. I think it's actually not a coincidence that the two systems that have been doing reasoning on stream processing, instance is implemented in Common Lisp and then Etal is on Prolog. And both of them are languages which are very nice for reasoning and which have some built-in support for expert systems and rule systems. But they are not known as the most performant languages. But for instance, this current implementation is only using a single core. Laptop would have already 4 cores, and Esper is using a multi-core approach, so it's already greatly winning there. Then at the moment the Rete engine is not modular, so for instance in the example from the third publication where I had all the event processing agents that were introduced, all the 8 ones running simultaneously, that was in one Rete network. And putting those all together creates a lot of comparisons and a large network. So in my results I could see also that running each one of the event processing agents separately and looking at the combined result compared to this total set of 8, then the individual EPAs are performing faster. And it wouldn't be a big task actually to modularize this Rete engine so that each EPA would run in its own network, as long as we don't need further interaction than perhaps memory and triple store. Then that would be a very good way. We could parallelize the hardware if we can parallelize the problem somehow. Anyway, instance is also RDF in and RDF out, so we can chain and we can split those streams as much as we want. And then on that example in the fourth publication, which I have mentioned now in passing, we did a preliminary test at indexing that comparison, which was doing up to 1 million comparison every time the time moved forward, and the speed improvement was 86 times, so we went from 20 EPCs per second to 1,736 per second. So it was a very good optimization in that case. But then this indexing slows down the processing in cases where it's not needed. So to really make this automatic, you would also have analysis capabilities in the platform to understand that which are the indexes that you should actually be sorting for this kind of process.
So, yeah, it was a later question, maybe more detailed question, but since you mentioned, can you maybe go back to the slide in which you compare the implementation of instance and Esper? Okay, so I was wondering whether there is an easier way to implement these in Esper using pattern matching. So Esper enables you to write pattern matching, which you can say, okay, I want to have something in a given time span, not preceded by something else. Would it be possible without using explicit windows? Do you think that this is something that EPL can offer, or if not, can you maybe elaborate a bit more on that?
At the time when I coded this, I went through the Esper reference manual and tested various different approaches. Then I asked Esper directly, and Thomas Bernhard, the CTO of Esper, about some of the key solutions there that are these, how they would do this, and do they have another way of doing this. And they at least assured at that point that this is the proper way. And then after I had finished the simulations for the publication, and I saw actually the main thing I was wondering was that for the fifth experiment where we test the whole logistics chain, Esper was slowing down surprisingly much compared to itself and compared to Instance, which didn't slow down very much from experiment 1 to experiment 5. That is there something that we could optimize about this Esper application? And that question was processed by Espertech for some time. We had a couple of emails going back and forth, and at that point at least their conclusion was that this is the way to do it, and they didn't have any proposals on that. So other than that, because I haven't now then tested that would the Esper pattern matching support this, I'm also wondering a little bit now that how has the pattern matching approach in Esper developed, because this was being done in 2013, that have there been changes since then which could enable another approach now?
That's interesting. Going back to my first question, that's interesting because Esper is offering a higher level abstraction, but sometimes when you have to do things like that, you have to rely on lower level abstractions and write your own windows and use windows as basically variables pretty much in the same way as you're doing instance. So maybe, I don't know if you agree with that, it means that we are not really there into finding a good processing abstraction, general universal processing abstractions for streams.
I think the issue is always in the details, that when you define a higher level abstraction, it's very difficult to take into account all the cases and all the possibilities that people might want to use it for.
Then, you already mentioned something in your presentation, but I would like you to elaborate a bit more on the difference between instantaneous events and interval-based events, and maybe better motivate your choice in modeling events, because it's a debated choice in the community. So depending on the system, you find different definitions of events and different definitions of timestamps for intervals or point time.
Yes, I think as for me the main motivation has been the timeliness. So in my view, event processing should really happen as fast as we have some information that we can pass forward. And also in event processing, it's quite a common understanding that events are not retractable. That once you have sent an event, you cannot get it back because it's going somewhere in the system. You can always send another event to correct what you sent before, but the event that you create presents your best understanding at the time when you have generated it. And now this concept of having an interval means that we knew something at the beginning of this interval, but we didn't tell anyone. We kept it to ourselves because we waited for this end time before we told anything. And I think often in stream processing that means that we are too late, because whatever it was that we wanted to observe in the system has finished because we waited for the interval to close. But then in this kind of approach, I do have the benefit of having structured events where also my definition includes that there can be multiple timestamps. So nothing prevents streaming also events that describe intervals. That event will be generated at a time point, but it will describe some state that took place in the past and that had a beginning and an end. And those can of course be streamed. So, and there are plenty of applications where that should be done. Does this somehow motivate my choices?
No, I must say that I totally agree with you. Indeed, the system that I wrote during my PhD uses point time semantics, and I totally agree with your motivations. then I was wondering, so you mentioned time and the fact that you can have multiple timing information, so when an event is generated, when an event arrives, and something like that. So time, especially in CEP operators, plays a central role, and often systems are highly optimized to take time into account. So they use time, for example, to prune all the information, or they index events over time, and so on. So I was thinking, do you think that this choice can have a negative impact on performance? It's of course a trade-off, but maybe you can elaborate a bit more on that.
Yes, and I think it most definitely can, but it also depends on how your implementation is being done. So if we take the example of SysParkQL, which is a very well-known platform for processing streaming SparkQL, I think at least the original implementation was basically gluing together two different systems, that it is using Esper to split the stream into windows, and then Jenna to run queries over those windows.
Yeah.
And in that case, it would be terrible if the timestamp would be inside the event, because at the point where the streaming window is being split, then there is no other need to go into the RDF and check anything from the RDF internal. So I think it's safe to say that always when your first operation is the windowing operation, then the faster you can access the time, the better. That should always be true. But then the penalty, for instance, in the case of instance, is not very big, because we are on one platform and we are just processing the SparkQL into the network anyway. So this doesn't add overhead that one of the triples that is being input is indeed time, and another triple that is output.
So you think another attribute would be the same? So let's be processing time or processing another attribute would have the same performance overhead.
Yes, although always what is spending time depends on your query network.
Mm-hmm.
Just reading the triple doesn't, or that spends some constant time, but then depending on what it does in the threaded network depends on the queries, and that always varies depending on what kind of operations you have.
Then, so you often refer to IoT applications, and IoT applications and in general event-based applications are often distributed. Do you think that your work can be easily extended to take into account distributed, but also you mentioned before parallel implementations? How would you do that? And do you think that this is necessary for many applications and beneficial?
I think it is definitely good and needed, and in a typical sensor application you have simple lower level sensors that are producing a lot of data, and there may not always be the need to propagate all of that data to higher levels. So we could use, for instance, multiple instances of instance on the lowest level to go through these simple sensory events, and then, for instance, report only the kind of changes that we want to know. So abstract already on one level to higher level. And then have a smaller number of, again, instances of instance running those streams and generate another stream, and then build this in succession. And as I mentioned in the presentation, because we have RDF coming in, RDF coming out, then there is no restriction as to what we can do. The only question is that what are the problems that we can parallelize, and then at the moment the platform doesn't have any automated method for doing this. So the query networks on various levels would still need to be written manually and the system built manually. I mean, normally nowadays in massive parallel systems, you just say how many machines do you want this problem to run on, and then everything else happens automatically. There is nothing such yet on this test plan. But of course that could also be implemented as another level.
So there is some research going on in stream processing in that direction on automated placement of the operators. So maybe do you think that these can be applied also to instance?
I don't see why not.
Okay.
And then also, since you asked about this IoT applications, then the World Wide Web Consortium is nowadays actively running an initiative called Web of Things, where they are defining Internet of Things to happen over web technologies, and there this kind of RDF-based also events are playing an important role in that work, and they also have stream type communication there. So it looks like that also elsewhere there are now specifications coming where you could do Internet of Things over the kind of technologies which I have used in my dissertation.
So another question related to scalability. So if I understand correctly, your approach currently stores all the graphs in main memory. Is that correct? Okay.
That's correct.
Do you think that these can, or now or in the future, be a limitation in some scenarios, and how would you overcome such limitation? So offloading to disk, how, or mainly going to distributed memory, shared memory systems?
Depends on the application, but then basically we already have some means to interface with a specialized triple store. Like I showed also the federated query in publication 3. That's not a very efficient protocol for doing it yet, but that's one way with which we could interface to a disk-based triple store already as of today, and access things from that. And of course, anything that we stream out at the moment can be directed to this triple store, over which we can make service queries then. But if that is a central part of the application to use that kind of storage, then most likely we can develop more optimized ways to do it. At the moment it would run over HTTP because these SparkQL service queries use that. But if you do it locally in the same machine, it's not going to be a very big delay. But nevertheless, it is something that could be used in the beginning, and then better optimized solutions could be found.
So do you have any quantitative analysis of this, of the cost of this application that you remember?
No, I haven't tested locally. So this service query was only tested to backport over the internet, and that is basically depending on both our network connection and then their server speeds. Local storage hasn't been tested yet, okay. So that would be the subject for another paper.
The overhead. Yeah, of course. Then something about, so I was a bit surprised not to see many quantitative comparisons with Windows-based stream reasoning systems like SparkQL. So you have something in the first publication, but just a couple of queries. So I would like you to elaborate a bit more on this. So if I understand correctly, it is fully possible to mimic the behavior of those systems in an instance. So I was wondering why you didn't include many experiments about that. Also because of the community you were referring to. So I thought that for the community it would have been easy to compare with systems that they know better, like SparkQL, SQLs, others.
Maybe I can show a little example, because I was preparing also to discuss this. So here is an example of an event pattern. That we say that we have event A, and within 30 seconds we shouldn't have event B. This is a basic negation pattern with a timer, and we have to have some time restriction because we cannot wait forever to see if there is no B. Now, if we try to do this with a data stream processing system with windows, then depending on how we position our windows, here is an example where our window would have an A and no B, so we can detect the pattern there, but it's a false positive because the B would have arrived after the window. Then we have an A here without B, which means that this is really the pattern that we wanted to detect. But once we have overlapping windows with different starting points, we very easily detect duplicates, which we should again filter out. So once we go into an event processor like Esper, every time we get an A, we insert it into a 30-second event originated window, and if we find a B, we remove all of the A from this window because this means our pattern didn't work out. So once we have the matching pattern, once an A exits this 30-second window without any B's showing up, we know that we have detected these patterns. And I think this illustrates the difference in the problems that are attacked with this kind of systems. So data stream processing systems are necessary for calculating aggregates on the stream. So to do statistical processing and to clean up noisy sensor data, you can average windows of data to clean up something in your input. And in the semantic web or the RDF stream processing community, that's what everybody else was doing. And if I would have gone there with instance, then my solution for that is more complex because I didn't have the higher level abstraction for Windows. And as for the true crunching power in processing those windows, I have all reason to believe that it would have been less efficient also, or at least for the case of the others, I hope it would have been, because they are specialized on that. But what I wanted to study are different kind of problems which deal with event patterns and have exact solutions. On the RDF stream processing community group mailing list, Professor Avi Bernstein from Switzerland presented this example of a student cafeteria where we have the door sensor going into the cafeteria and then the door sensor going out. So with data stream processing, what you do is to count some average of the net arrival rate within some period of time, and then make a graph out of that and post that onto a website so students can estimate from that graph that is this a good time to go have lunch. And the kind of event processing thing that you would do with that data is to count exactly how many people are in the cafeteria and bar the gate if it's full. And also show a counter on the website that this is how many people are in at the moment. So the problems which I wanted to address were of a different nature, and then going further into these kind of statistical applications for data stream processing would not have progressed to work on that kind of problems, and most likely it wouldn't have been lucrative because the solution would have been more complex, and then probably the efficiency wouldn't have been competitive either. So it didn't look like a good choice to go further into that.
Coming from the community of event processing, I fully agree with you. Yeah, I was just wondering why not say, okay, I have the same expressive power, and indeed I can mimic your behavior, and maybe I 10 times slower, but nevertheless I'm not specialized to that. I was just wondering about this approach, let's say, to present the results, but I fully agree with you.
I wrote a generic SparkQL library on which you can define different types of windows and process those. So it exists on the instance GitHub, but it never made it to a publication.
Okay.
But the groundwork has been done to demonstrate it.
Okay, I will check that. Then I'm sure you are expecting this question. It is SparkQL, so it's another system that basically somehow overlaps with part of your research because it combines semantic web standards and complex event processing. Can you elaborate on the differences between your approach and the SparkQL approach?
EP SparkQL, as far as the publications are concerned, was concentrating on the event sequences and processing of sequence of event. There were some specific cases, and actually I really would have liked to compare with that platform, but then the development of EP SparkQL stopped fairly early on, so there were some characteristics of SparkQL 1.1 which didn't make it to EP SparkQL. So with the outcome that my cases couldn't be really run on EP SparkQL. Now it's another question then that could they be executed on Etalis, which is the prolog-based solution behind. But also the development for that had stopped, and it was difficult to find an executable version which could have been used. So then in the fourth publication, when I really wanted to do event processing and compare with an other application, it appeared that Esper would be the more safe choice to go for in that point of time. But otherwise, I mean, if the development of EP SparkQL would have continued, then it would have been the closest one of the current platforms. And from the documentation, it looks like it would operate also without these time windows. But in the published examples, there are no such cases, that the published examples are all operating on Windows.
Then another question is, do I understand correctly that your rule evaluation algorithms does not have guarantees in the order in which the rules are executed? So there is some non-determinism. You could execute them in parallel with that.
That's correct.
So this non-determinism can lead to different results in different executions. You, for example, to raise conditions in the order of read and updates the graphs. And how can you guarantee correctness under this non-determinism?
At the moment, I think the only way for the programmer, if you have this kind of condition which is impacting the end result, is to code something in the memory that you update based on which stage you're going on. So implement, in a sense, an execution order for the rules. If it's not critical, then you just let instance process in any kind of order it wants. But if it's critical, then use some memory, for instance, to define that now we are at step 1, and then update that, and then its rules for step 2 will trigger.
So basically, you have to implement the locking system or something like that.
In those cases, yes.
Okay.
And I think
synchronization, more in general, synchronization mechanism. Okay.
The most common and I think the most tedious such issue that came up is the point of optional information in events. Because as soon as something is optional in the event, it means that you have multiple different results based on whether that optional element was present or not. And this you can usually remember in coding the application, when you're reading in the data, that you are careful that you have checked whether these optional elements are present or not. But then when you remove such an event, then there is a possibility that instance starts removing things from the optional elements, in which case the rules that are expecting something from this event trigger again, because the event changed. So in those cases, one solution is to change something in the mandatory fields of the event so that it will no longer match with those queries before you delete as a precaution. And of course, this is something that shouldn't actually be the programmer's responsibility. So it would be very nice to develop something there that would give more security and make the tool easier to handle.
Okay, then maybe we can move to reasoning. So my first question on reasoning is, you compared instance with static reasoners. So I was wondering what is the exact semantics of reasoning in that context. So in particular, when did you consider materialized information to expire, and how do you make the comparison with static reasoners fair?
In the case of LUVM, the creator of the benchmark has released the sample results for one university. And I looked at the complete results produced by instance and produced by these static triple stores, and verified that they produce exactly the same result. Now, how I made it a stream, for instance, was that I was looking at each, or maybe I should say first this are you familiar with the LUVM?
Yes.
Okay. So it has university departments coming in succession, and it turns out that there are no queries which would require multiple departments to be present at the same time. The result is still the same if you process each department individually. So that's then what I used as an event in instance. I found a triple which comes in the beginning of every department and used that to clean all the materializations and the original triples from the previous department.
Okay.
It's a little bit of a hack, but the issue there was that looking at the actual stream processing and stream reasoning, then some of them provide some RDFS reasoning, but with limitations. But I didn't see any other stream processing platform that would have had, for instance, O2 RL reasoning. And some queries in LUVM require more than RDFS. So I wanted to test more than RDFS on instance, and I wanted to compare it with something.
Yeah.
And then the only thing to go to was these static triple stores.
Yeah. So you mentioned something about event-based memory handling. So for example, that you use this department to switch from events to static processing. So if I understand correctly, this whole mechanism is application specific, and is up to the developer to identify places in the application where you can get rid of the previous materialization and start over. Is this correct? And do you foresee any possibility to make the process more automatic?
For the first question, yes, the way that it was built here was specific to this application. But I also think that the part that it was somewhat unnatural was because this data wasn't really an event stream. It was something else here. So with a real event stream and reasoning on that, it would be easier to build this kind of a mechanism. But then to automate it further, I think as instance is at the moment, then a fairly generic library could be built since we can use some kind of predefined RDF data to explain where the time code is found or how to separate between changing events. But then also what I think is important in this, that the mechanism that you can use for deleting current materializations or event information, it varies from application to application, and it varies a lot also within the application. So in the same stream processing task, you might have some events that have to be kept for 10 seconds, some often arriving, and some which you would want to store for the whole year because they are related to some seasonal changes. And in that way, whatever mechanism is developed, it would still be good that it would be specific enough that you can differentiate between the storage classes for the data and how long you want different types of data to be stored. I have been also talking about implementing some kind of expiration times for events, but for that purpose we should first have the understanding of events in instance, because at the moment, as I said earlier, the concept of an event exists in the queries. So we should first take that into the data, into the written network, then we could define the lifetime for the events and have a more automated mechanism there. Until such time we're dependent on the queries.
Okay, no, I perfectly see. Yeah. So another question on reasoning is that you propose a materialization-based algorithm for reasoning. Can you discuss the differences with respect to backward chaining, with writing algorithms and motivating your choice?
In forward chaining reasoners, basically you take the data you have, you apply rules, and then you see whether the decision that you, or what kind of decisions have you arrived at. And in backward chaining reasoning, you start basically from the decision, and then you verify rules and see whether your data supports the decision where you started from. And I think the choice in this case was dictated by necessity, because for instance at the moment we didn't have the tools to do backward chaining reasoning. So it's more, I guess Datalog would be the kind of language where you would have this kind of properties. For SparkQL it would have needed to be developed separately, but then the query network approach that we had was suitable for materializing reasoning. As for the comparison then, I chose Stardock because that has a faster reasoner that is not based on materialization, and then compared with that. And really what was found out was that performance-wise it is clearly superior. So if the performance is important and there are resources for further development, then certainly backward chaining reasoning should be looked at, and updating the queries instead of materializing the data, because also then for stream processing, materialization is actually not a very good approach, because materialization is good when the data doesn't change.
Yeah.
You only need to materialize once, but then for a stream you need to materialize all the time, and that then introduces this cleanup issue which I have then dealt with.
So am I correct to assume that you foresee significant performance improvement if you move from materialization to query rewriting or backward chaining in these kinds of applications?
Yes, definitely. Then the work is done beforehand, and the queries are already there, so no need to spend time doing the stream processing for materialization.
Okay. Also, so in your reasoning, you were basically removing all the materializations about one department and then starting over with a new department, right? So there was no overlapping between the reasoning that you were doing with one department and the reasoning that you were doing with another one, right?
That's correct.
But in several applications, I expect that there will be some overlappings, and there are indeed some tools that do incremental reasoning, because you basically do the incremental stuff. So you remove something and then you add something. You don't start over from scratch. Did you think about comparing with those systems? Do you think about considering these scenarios? So I'm thinking, for example, about ArcticFox, which is a static reasoner that includes incremental reasoning. Can you maybe elaborate a bit on this?
Yes. For this application and LUVM, this scope of a department was suitable, but then, as I guess I also mentioned before, in different kind of applications, you might have different events or different kind of data with different time scopes for the materializations, and then it should be implemented in such a way that you can support each of those durations, and the kind of longest time that you would need to make the materializations available for them to be useful. But then, as for incremental reasoning, I think really also need to be mindful about doing stream processing on an infinite stream. So we can increment our recent result base to some extent, but then if we want to process an infinite stream of data, we should also have some limitation of how long we can keep certain data in the system.
You need some concept of validity, so you can derive some state and then have some concept of validity of the state. Maybe that can be then treated by events, the dynamic event, and also delete previous state.
Yes.
But that would need some theory at a higher level to decide how events influence the current state of the system.
Or such an example and an analysis of the example that how long do you need to keep the materializations resulting from each event.
The final question about reasoning is so the intelligent regimes are well defined. So it is somehow, and it has been shown in previous publications, that it is possible to define ad hoc algorithms explicitly designed for specific rules and for specific regimes. Can you elaborate on the benefits of using instance instead of these ad hoc algorithms, for example, for RTFS or for other regimes? So the questioning about the motivations basically behind publication 5. So why do you think it is needed to ground these reasoning operations of your proposed approach in networks of smart productivity?
My motivation at the starting point was to test if it can be done. If I can indeed implement compliant reasoners on a network of SparkQL queries and see whether that is possible. And then once I dug deeper into the compliance tests and the different benchmarks and even some industry implementations, it turned out that there is a lot of variation as to how different parties are implementing these entailment regimes. For instance, because some of them create a lot of materializations in the system. If you feed any triple into O2RL, I think it materializes more than 100 triples based on each incoming triple, even if it doesn't particularly match anything in the system. And so what emerged as a very nice thing is that since everything was still SparkQL, the queries were SparkQL and the rules were SparkQL, then whoever is familiar enough with the platform to write the queries can also see the rules. And the rules can even be packaged together with the queries in the same file. So then it is very easy today to do task-specific optimizations on the entailment regime. And of course, it will always be stated that since it has already been proven that a certain entailment regime has certain properties when it's complete and fully implemented. But still, looking at the compliance tests, which test up to 17% of the rules, or LUBM, which uses 3 rules in any given test, once you have the understanding that what is needed, then this approach gives complete flexibility to implement only what is exactly necessary, and then to make sure that even if there are further releases, for instance, from instance, then the rules are still packaged in your own package with your own queries, and you know that nothing changed in that area. Now, I may not be able to analyze completely how this relates to the ad hoc implementations there, but I think that's kind of my view on what is good about this approach. What does it enable?
Thank you. So I think I'm done with the difficult questions. Now a very difficult question. A broad question on the overall research domain. How do you see string reasoning evolve over the next years, and which aspects do you think that deserve more investigation in this area?
Specifically reasoning?
No, I mean string reasoning, meaning in general stream and event processing combined with RDF and reasoning capabilities.
Okay. For me, one of the main issues, and I think this is not personal discovery, a lot of other people have noticed this as well, is that there is still too much fragmentation in the field in defining, for instance, what are streams. RDF stream processing community group has been trying this for a while. So my solution to this would really be to go and define this specified stream description with which we can really describe what are the contents of a stream. And once that is understood by the platforms, then also building reasoning on the top of that would be significantly easier. Now, for reasoners, there is lots and lots of theoretical study and papers, but then when you start to look for actual implementation test cases, and especially in the round of reasoning, then I think there should be room for some really lucrative use case papers also in a sense, because there are not many of those around yet. So in a sense, I think a good step would be to concretize the streams a bit more, and in the reasoning side, apply the theory that we have and show really what it can be used for in a stream set.
Okay, thank you very much. I think that these conclude all the questions I had on your thesis.
Do you have a closing statement?
Yes. So thank you very much for your answers. They fully answered my questions. To conclude, the thesis addresses an interesting and increasingly relevant topic. It addresses this topic with scientific rigor and provides novel contributions to the research domain. It clearly discusses the motivations behind the research, the state of the art in the field, the design and development of a novel solution, its assessment with critical analysis of the advantages, limitations, and open research issues. So thank you very much and congratulations on your work.
Honored Professor Markara, I sincerely thank you for your observations. Ladies and gentlemen, I ask those of you who have observations to make on the dissertation here presented to kindly request the floor from the pulpit.
No observations. Okay, so anyway, thank you, Professor Magara, for being really giving us a good grilling of the candidate and for your insightful comments. So, if there's somebody in the audience, or you know somebody who would like to make an official comment on the dissertation, you should basically inform me right after this occasion. So otherwise it wouldn't be considered by the university as an official comment anymore, and your only way to kind of play the game, if you so want to say it, is open your mouth now. And so after saying maybe this was the well. But anyway, otherwise I thank you all, and